Without further ado, I'd like to introduce our speaker today, Fermin Serna, and today's presentation is the info leak era of software exploitation.
Thank you. Good afternoon. Thank you for coming for my talk. Again, hopefully you got a lot of coffee. This is going to be an interesting one. My name is Fermin Serna. Today I'm going to talk about Infolics. Before going deep into my presentation, I want to get some information about the audience. Can you raise your hand? How many of you have ever exploited a stack-based buffer overflow, EC1, in the 2000s? Okay. That was not expected. How many of you have defeated NX or DEP, exploiting that one? How many of you thought that in 2004, when XP Service Pack 2 introduced DEP, the end of exploiting was over? We should start a new gardening business or something like that. At least I thought it. And right now I take a look to those days and I laugh to myself. And then later on, ASLR came, and I made the same mistake. I thought the exploitation days are over, but no. The thing here is that as long as security researchers, either defensive or offensive, they keep doing research, they will always find small tweaks or small areas where the mitigations are not as effective as they thought when they were developed. Nowadays, that we have full ASLR, DEP, and all these things, one of the new hotness are Infolics. So this is a talk about Infolics. So this is the agenda of today. Basically, it's divided in three areas. You see two over there, but it's three areas. The first one is talking about what is an Infolic, what it was not needed before, what it is needed right now, some examples. I'm not trying to claim that I'm inventing or researching all these techniques. Some of these, they were already applied to exploits even 10 years ago. I'm not claiming anything. Some of them, yeah, they are original, but not all of them. So I will try to make examples of exploits that they were using particular techniques. But just want them to be clear on this. I'm not claiming ownership of anything. Some of them are original, some of them not. I will try to make sure which one are which. Also, and then we will go deep into the technical details of this talk, Infolic Techniques. The idea here is to convert type of vulnerabilities into an Infolic. Not all of them will be convertible to an Infolic, but some of them will. I'm just going to give you some general techniques and general hints to try to convert those. Those are going to be totally dependent on the vulnerability. Some of them, they have some requisites to meet, and without meeting them, you are not going to be able to convert them into an Infolic. Here is a list. We're going to talk about heap overflows, stack overflows, use after freeze, type confusion vulnerabilities, and later on, it's not an Infolic, but I found it so cool that I had to talk about this. It's converting a use after free into a universal XSS. And you could say, what the fuck is this guy talking about? Converting a use after free into a universal XSS, a memory corruption into a logical bug? Yeah, you can do it. I will present in deep detail a vulnerability I found in Flash in March that, by the way, is going to be in the Pony Awards. But I don't have any hope because of Pinkie Pie and Alexander or something. Or no, Sergey something, sorry. How I converted that information, that vulnerability into an information disclosure vulnerability. Back. And later on, some slides about what I think exploitation is going to be in the future. So, who I am, I'm Fermin Serna. That's my Twitter, that's my email. Feel free to contact me with any question or feel free to talk to me later. I work for Google. All this research was done in free time. Google just gave me the freedom to talk about this as long as I'm reasonable. Before Google, I was working for Microsoft at MSRC. I was the main developer and owner of Emmet. Who do you guys know? Who knows about Emmet? Who is using Emmet? It's an awesome tool. They just released the new version today. So you guys should check it out. And I've been writing exploits since 1999, so I think I'm a little bit entitled to talk about exploitation techniques. Let's go deep into the details of the talk. What is an infolic? The problem here is I couldn't find any definition of infolic totally, on exploitation. You could find infolics on some other sciences, but not on exploitation, so I had to come with mine. So yeah, I'm quoting myself. So an infolic is the consequence of exploiting a software vulnerability in order to disclose the layout or content of process kernel memory. I want to make emphasis on the layout or content. It's not always about getting the data on a specific address. It's super useful when you get information about where is the heap or how the heap is, what's the layout of the heap. That's my definition. Also, we have Halvard Flake, and I fully agree with him, is that you do not create an infolic. You do not find an infolic. I mean, it's not that you start fuzzing your favorite browser and you find an infolic. You create an infolic based on a bug or vulnerability that you previously found. And infolics are needed for reliable exploitation. ASLR bypass is a subset of reliable exploitation. Because back in the days where ASLR was not present, infolics were used for reliable exploitation, for locating your cell code or something like that. So yeah. Why they were not needed before? Because back in the 2000s, we were amateur exploit developers who were jumping in to fix it, addressing the stack. Who remember the get_sp C snippet of code where it was getting the stack pointer and you use that remotely? It's like, if you do it right now, probably I would, chuckle. We were lazy. On 32-bit, you can, in the context of a browser, you can spray 2 gigabytes, and most likely 41 is going to contain the data that you are looking for. And there were generic ways to bypass mitigation. So for example, if ASLR was not present, but deb was present, or NX was present, by performing return-oriented programming or returning to libc or whatever, or any other of these techniques, you could bypass deb or NX. There was also non-ASLR mappings on Windows. It was an opt-in thing. If you don't compile your DLL with the ASLR thing, it's going to be always in a predictable place and JIT spraying, but this is kind of gone. So yeah, amateur, lazy, generic ways. Why they are needed now? Because some people need reliable exploits. Those people, your guys are clever people. There are new security mitigations, such as, for example, in Windows 8, there is mandatory ASLR. You can use emmet for enforced mandatory ASLR. On Mac OS, Lion and Mountain Lion and all these new weird animals. There's also mandatory ASLR. Unix, long time ago, they adopted it. Again, Infolics, nowadays they are more focused on bypassing ASLR, but my opinion is more for reliable code execution. And those generic ways that we were using back in the day, such as .NET, Alex Sotirov from Argot, .NET Trick, or .NET 2.0 on IE, all JIT spraying from Dion, they are all gone. There could be some generic ways, but yeah, I don't want to talk about that here until they are probably fixed. And here's a previous list, a list of previously used Infolics exploits. I'm not going to go in detail on all of this. There is tons. There are Infolics that they were used even 10 years ago, so it's not something that is invented right now. Again, I'm not claiming that I invented any of those. Some of them they are original, some of them not. I will go one by one, trying to detail which one is which. But lots of people, they were involved in this long time before me. There's a nice list. I want to make some emphasis in, for example, all the Pontuons, IE vulnerabilities, and Firefox last year, they were using Infolics for bypassing ASLR. And for example, there's a nice browse and get on scenario that the Duku exploit used for a kernel, using a kernel vulnerability, and at the same time using an Infolic for reliable code execution. So yeah, you can check out all this list later. Let's use this as an example. This is a super small snippet of source code. Main function with guess where it is, the buffer overflow highlighted. So yeah, let's use this as an example. It's a stack-based buffer overflow. We're going to overflow the buffer, the 64-byte buffer. This overflow is inside a try step. So let's assume that this is on Windows. So the stack is going to be buffer, other member variables, safe EBP, safe EIP, argument, something else, an extractor exception record in the stack. So if there are no mitigations in place, this is like 2000s, early 2000s. So we just overwrite EIP, return to our shell code. There's no NX, there's no ASLR, nothing. I'm not going to give information on what these mitigations are. I assume you guys know about them. I don't want to spend 50 minutes talking about the ASLR. I assume you guys know about this. GS, canary cookies, so yeah, you can, instead of overwriting EIP, you go to the extractor exception handler registration record and you overwrite the handler and you jump into your shell code. If GS is enabled and dep is enabled, you do the same, but instead of returning to your shell code, since dep is enabled, you return into libc or you do your ROP or return into programming or whatever technique you feel like. If SCHOP is enabled, you can do the same, and at the same time, SCHOP basically validates that the extractor exception registration chain is intact. You can fake it because ASLR is not in place, and you can predict where it's going to be the final record that contains the canary value. And if everything is enabled, GS, dep, SCHOP, and ASLR, basically you either pray or buy a good Infolic or find a good Infolic. So that's the key of this talk. Nowadays, they are needed because of these super nice people in OS, in the companies that they develop OS, they are making this harder, which is good. So let me check the time. OK. Infolic Techniques. In this talk, we're going to talk about techniques. And I'm most likely, I will try not to refer to browsers, but most likely I will. So just this is a heads up in advance. But you can apply this to any process that exposes some primitives that an attacker can use. These primitives is, for example, you exercise some type of code. I don't know. Imagine on JavaScript, you create an element, an image stack. And by creating an element, an image stack, it's going to translate into some allocations in the heap, some frees, etc. So as long as you find a way to translate an action in the process into your primitives, you can apply all these techniques to this type of processes. So you need an alloc primitive, a free primitive. When I mean an alloc, is an alloc of a specific control size with control content. A free is freeing something that you control, a pointer that you control. Also, if in case I want to create a specific type of object, I want to exercise some functionality in the program that will translate later into allocating this type of object. And optionally, most of the times needed, I need heap spraying capabilities. Heap spraying is usually linked to JavaScript, but this is not always true. You can heap spray through images. You can heap spray through a lot of things. And not only heap spraying, it's super useful to read back the heap spraying that you made. So on JavaScript, it's super easy. You just have a huge string, and you can read it back from that variable that created a huge string. Examples that they are really, really well researched basically are the web browsers. They are really, really known techniques on how to allocate memory, free memory, massage the heap. We will later define some terms. Flash, it's really well researched. This is because it runs mainly everywhere, and it's super useful if you find a Flash vulnerability to exploit any host process. But generally speaking, any host that can run attacker control scripting. So any host of a script language, but it's not limited to it. For example, you can find these primitives on Excel by parsing BIF records. An Excel file is basically a list of BIF records. Excel is super nice when you parse on a specific type of BIF record. It will allocate some memory or it will free it. So you can have an Excel file that it will allocate 10 strings, it will free one. I mean, depending on the BIF records, but yeah. But this talk is more like on the browser. But you can apply this again to any process that meets these requirements. I'm going to define some concepts before continuous execution, because I'm going to use these concepts later on. Basically, continuous execution, yeah, sorry for my definitions. I'm from Spain. This is not my native language. But I define it as the ability to gain control of the flow of a program, execute a cell code or a gadget or something that you control, and later give back control to the program. So the program does not crash. So it's like, okay, I exploit a stack by use after free, something executes, but the attacker, the user that is being attacked does not know anything. The browser doesn't go away. I mean, it's still in the same page. So exploiting someone, giving back control so you can exploit it several times. Heap massaging, this is something that we're going to use later, is the ability to influence the heap layout of a program by controlling where an object is placed and what is adjacent to it. So basically, I'm going to use the primitives to control the layout of the heap. I want this object to be surrounded by these other two objects that I control. And use after free, use of previously freed memory, you should do to a dangling pointer reference to a free memory object. Super simple version. So we create an element. This element is in memory is going to be a C object. It's going to have a B table pointer. That is going to a B table pointer is a pointer to a table of virtual functions. This, excuse me. This is going to point to a DLL shared object or whatever. And later on, it's going to have member variables. So if this object contain, I don't know, for in this case, and several variables from insignificant, long, flags, char, buffer, another type, cache, and later on an array of 64 bytes. All of this is going to be part of the same memory chunk. The first 4 bytes or 8 bytes, depending if you're in 32 or 64, is going to be the B table pointer. So this is when we execute this JavaScript code, document create element image tag. Again, this is super simplified. This is the blue square is the memory that contains that object. So if we later, by using a vulnerability, we cause the free of this memory chunk, but the variable A still has a reference to this memory chunk, we basically trigger the use after, well, the free of the vulnerability. We not yet exercise the code that is going to use it again. So at this point, the memory chunk is free. Most likely, the first 4 bytes or 8 bytes are going to be changed because depending on the heap implementation, it's going to be linked to another free chunks. Depending, but for simplification, I didn't do anything. Basically, the contents are the same, but the block is free. Using a primitive in JavaScript, locating a string, we are going to reclaim that object. So the attacker not only controls that object, but controls the content of that object. So for example, right now, A is pointing to this, the variable A, the JavaScript. Behind their functionality is pointing to an object that is pointing to here. Right now, the attacker controls the B table pointer, 41, 41, 41. This is because of AAA. And not only controls the B table pointer, but controls all the member variables. In this case, flags, buffer, long type, cache, and name. So this is key for the rest of the presentation. It's not about controlling the B table pointer. Back in the days, back in the 1-2 years ago, people were only focused on controlling the B table pointer because that's the only thing that they needed. But for Infolics, we need to control the member variables of the object. So in this case, the attacker allocated a string. Probably it's not going to allocate one string, it's going to allocate thousands of strings because they want to reliably get this object. And later on, it's going to exercise of some functionality on JavaScript that it will exercise that reference. There are several different types of functionality. The first one is a virtual function of the object. A virtual function of the object is going to get the virtual table pointer, dereference it, and call into it. We're interested in those. They are super cool. But right now, if it's going to call into some place that you control and you don't have any information about where are the modules, it's kind of useless for right now. So there's another scenario where we're going to exercise some code, but that code is not going to go through a virtual function. It's going to go through a non-virtual function. So it's going to jump directly into a module passing probably ECX as the this pointer. So it's not going to dereference nothing from this object. It's just going to call over there. And what happened next is up to the implementation of that object. There are some other scenarios where they will directly inline something for grabbing a variable or something like that. But yeah, use after free, create an element, somehow free it. That's the vulnerability, the red part. The attacker will allocate something. It will not only control the virtual table pointer, but the other member variables. This is super useful, again, for the next of the presentation. And then exercise some code that is either a virtual function, non-virtual function, inline thing, or whatever, that will use this object as a valid thing, while the attacker is holding not only not only the chunk, but the contents of the chunk. So this talk is about the possibility of converting several types of vulnerabilities into Infolics. Some of them depends on totally depends on the vulnerability. Some of them, some techniques, they have some requirements. If you don't meet them, you either look for another type of vulnerability or another way to play with the vulnerability to find an infolic, or you just, I don't know, report it to the vendor. So again, types of vulnerabilities into kind of hints techniques. We're going to talk about stack overflows, heap overflows, use after freeze, type confusions. And later on, it's not an infolic, but I thought it was so cool that I had to talk about this. Converting a use after free, memory corruption, into a logical thing, universal XSS. And finally, we'll talk about this vulnerability in Flash. We'll go through a quick walkthrough of how I exploit it. And again, this is nominated for the Pony Awards at 6:15, but I don't have any hope. Stack overflows. In the picture that you're seeing, there is a stack-based buffer. This is the buffer that we're going to overflow. In the stack, there's going to be other variables, EBP that was saved with this concrete value, 10, 5, 6, whatever. It's going to be the safe EIP and function arguments. The idea here is that there is some requirements, and I will explain later why we need this. We need continuous execution and heap spraying. We need continuous execution because we are going to exploit this twice. The first time that we're going to exploit it, we're not going to entirely override the safe EIP value. We're going to override it partially. So we're going to land into, we control where we're going to land. In this case, we're going to land in a range between 7F E3 0000 and 7F E3 FFFF. The idea here is to land into a return-oriented programming gadget that is going to write back into our heap spraying. So continuous execution for executing the vulnerability twice. First one for info leaking and the second one for code execution. And the second requirement is heap spraying. The idea is we previously heap spray. We perform we partially override EIP. We return into a ROP gadget that is going to write back into our heap spraying. Hopefully, this ROP gadget is going to be in that page, basically between 7F E3 0000 and 7F E3 FFFF. If you find that ROP gadget, you're done. It's going to write into EBP. And again, I assume that there is going to be an interesting value in a register, in this case, EBX. So in this case, we're returning into a ROP gadget that is going to write EBX into EBP. But hey, we control EBP, in this case, 41, 41, 41, 41. So again, we need to execute the vulnerability twice. First one for info leaking, second one for remote code execution. Returning into a page of the binary into a ROP gadget for info leaking. Yeah, this is what it's called partial override. I'm not claiming that I invented this. This was used a long time ago for the NEI vulnerability on IE, and yeah, this is not news now. I will take questions later in the QA. So heap overflows. We have here a heap-based buffer. In the picture later on, we have a JavaScript string. Usually, I'm not focusing on any browser, but usually JavaScript is just 4 bytes or 8 bytes, depending if you're in 32 or 64, that contains the length of the string. The string, blah, and later we are going to require heap massaging because we are going to place the heap buffer that we're going to overflow, the JavaScript string, and an object. The idea here is to override the size In this case, the size is 4 because the blast string is 4 bytes long. And we're going to rewrite it with ffffffff. Later on with JavaScript, we are going to reference that string, and we're going to perform some operations in that string. In this case, string.substring something. And this JavaScript code is going to check the length. And since we overrode the length and it's super huge, we can read any place relative to the object. And in this case, we're going to target the object vtable that is adjacent to the JavaScript string. This also was used by Skyline in an exploit that he developed for Chrome, probably some others. Heap JavaScript string object. We override the size of the string.length to be able to read past the buffer of the JavaScript string. The second heap overflow also requires heap massaging because I want to play the heap-based buffer that we're going to overflow and another string and an object. In this case, it's not going to be a JavaScript string, it's going to be a regular string. Regular strings it's just a string null terminated. So in this case, you're clever people, yeah, we're going to override the null characters. So whenever we reference that string, it's going to return data past the blah and the null character because we overwrote it with AAAA. So it's going to give us all those A's plus what it is adjacent. And using heap massaging, we were able to place an object. And the first, as I told you, the first 4 bytes of the object is basically the vtable of that object. So yeah, again, this was used. This has been used by Bupen. This has been used by several other pwners. Use after free. Remember, we were talking about virtual methods versus non-virtual methods. Virtual functions super useful back in the days. Right now, I mean, if you don't have an Infolic, yeah, you're going to crash in on probably unknown place. So we are looking into use after free, where by exercising some code, you are going to end up calling into a non-virtual function. Non-virtual function, as you see in the second snippet of assembly, is not going to deref the virtual pointer, it's just going to jump into a module. And they usually push ECX as the this pointer. Not only for use after free, for uninitialized variables, if you, let's say that you have a stack variable that was not initialized and later it's going to be used. If you stack spray before exercising the vulnerability, you are going to be able to control the object, the pointer to the object, and it's kind of similar to a use after free. So again, we are looking for non-virtual functions, not for code that exercises non-virtual functions of an object that we already control through a use after free. Several examples in this case, as we said before, by controlling the object that was freed, and there's still a reference, we not only control the object, but the contents. And people were usually targeting the virtual table pointer. But in this case, we want to control all the member variables. In this case was used lately by Bupen for exploiting the XML vulnerability on AI. Basically, we have an object. It has its own virtual table pointer, but we're not going to use it because we're going to use a non-virtual method. And PTR is the only, this is a super simplified version of a use after free. PTR is controlled because we control the contents of the object. Remember the 41, 41, 42, 42. So probably PTR right now here is 42, 42, 42. So there is a non-virtual method F. There's going to be some, again, JavaScript, but could be applied to any other process. There's going to be some functionality in JavaScript that is going to call into this non-virtual function, and it's going to return some value. Hopefully, that value is later on going to be returned through JavaScript or by any other means. I know that Bupen, they were using their RGB colors for reading back memory, and they could reliably control where to read by controlling one of the member variables. Use after free with member rights basically is the same thing. Instead of reading, writing. The requirement is we need heap spraying, so we can later write a value to our heap spraying. The idea is we spray strings, And we, again, use a functionality of the program to exercise a non-virtual method that is not going to call into a virtual function. It's not going to derive the table pointer. It's just going to call into a module with a control object. So here, what is going to happen is going to OR something on over there. So if we put in PTR 41, 41, 41, 41, and we control PTR because we control not only the virtual table pointer, but the member variables. Sorry, I'm repeating myself, but I want this to be clear. So we're going to write into some place. By writing into some place, is most likely we're going to write into the middle of a string. Later on from JavaScript, we are going to read that string and we'll say, okay, that's super nice. 41, 41, 41 is offset 13 in my 20th string. So I perform again the vulnerability. So instead of writing to that place, I write to the string.length value. So we are again in the previous method where we could read and write any place relative to my buffer. So again, we perform the vulnerability once. We identify the address that we're writing is equals to this offset of this JavaScript string, and we exploit the vulnerability twice to override the string.length for converting this particular vulnerability in the previous one that we mentioned that it was a heap-based buffer overflow where we're overwriting the string.length. Another one, use after free. There's going to be a nice picture after this one, so don't worry about the wording. Requirements is heap massaging and predictable layout. This depends on the layout of the process. It probably is using Windows or Linux heap functionality, or probably they implemented their own one. There are some applications that they, in my opinion, by mistake, they implement their own heap. They should be using the latest OS ones, which on some OSs they are really good. They have good hardening measures and mitigations. So, but yeah, if you are able to heap spray and you are able to predict, massage the heap and kind of predict the layout of the heap, you can perform this one. The idea here is that we can free any pointer that we want. Again, we have here an object where we not only control the vtable pointer, we control the PTR. So if we exercise some functionality in the program that is going to call into a non-virtual method f that will not call, it will not reference the virtual table pointer, it's going to free some place. Again, we control PTR. We're going to free something that we control. The idea here is that we spray a lot of strings. As you can see here, we have the freed object with control content. So the table pointer, we don't care because it's not going to deref it. But the PTR, we control it. And if we can predict the layout, we can point the PTR to one of those strings. So by exercising the functionality, it's going to free that string. So at this moment, all these strings, they are there instead of this one. The malicious hacker or attacker or researcher or whatever you want is going to request memory. I mean, using all those primitives that I told you that they are required, is going to request this size of chunks, and hopefully one of them is going to he's going to get it. At this moment, I mean. Hopefully, in this case, he's not going to use strings because strings is just a string, is not an object. He's going to request memory by allocating objects, executing some functionality that will allocate objects. And by allocating an object, the first thing that is going to happen is that they're going to place a JavaScript, the vtable pointer over there. So we have a lot of strings that they are allocated. We have one string that it was freed, but we have a JavaScript reference to that string. And the attacker got that chunk that we freed through the use after free, and by allocating an object, and the attacker is going to be able to read the vtable pointer. By reading the vtable pointer, ASLR is game over. You just subtract the fixed address, and you redo I mean, you already have the base of one of the modules. It's game over. You probably redo the exploit with this information for reliable return-oriented programming or something like this. Yeah. The third step is reading back the object through the reference to that string in JavaScript. On-demand functions or pointers of vtables basically is the same thing. It's a non-virtual method where it's going to write back to your object something that is useful. In this case, in this snippet of code, we control PTR. And not only we control PTR, is one of the requirements is we need to read back the content of the object. The strategy here is that memory chunk claimed by the string. This is attacker control. He plays AAA, but you could place anything that you want. And later on, it's going to exercise some functionality in the application that is going to call into a non-virtual function, f, that is going to resolve WinSec. Basically, load library, get proc address. And guess what? It's writing back to PTR. So what's going to happen? PTR is going to be, the address of WinSec is going to be written back to the object that we control. And if we can read that object from JavaScript, guess what's going to happen? We already bypass ASLR because you subtract a fixed address and you have the base of that module and you are done. Again, these are super simplified things, but these are things that are happening in the exploitation field. Type confusion, this is the latest hotness. Basically, the idea is that you couldn't find any non-virtual method. All the functionality that is happening is through virtual methods. So basically, it's dereferencing the virtual table pointer and calling into some place. So the idea is, if we don't know it, let's make the program put something that is going to work over there. So we perform a use after free of an object X, but later on we reclaim that memory chunk with an object Y. And if that object, whenever you exploit the vulnerability, it's going to reference the virtual table pointer, but since the application placed in that chunk an object Y is going to have an accurate virtual table pointer, it's not going to perform an access violation by calling into a virtual function, and it's going to jump into an address of a module. What's happened? The problem is that what happens next after the type confusion is up to the application, and you need to find. It requires several steps. The first thing is that the virtual function that is going to be called in object X has to have the same amount of parameters of the virtual function X number whatever in object Y. This is because when returning from that virtual function, the stack needs to be in the same state. So if it had 3 parameters and 2 parameters, it's going to be off by 4 bytes. Or 8 bytes, depending on 32-bit or 64-bit. So again, everything failed, but yeah, there is still hope. Type confusion, virtual functions, we replace an object of type of something with an object of type of another thing. That is going to use, one of the techniques used before. So basically, it's going to load a DLL, or it's going to write back to JavaScript, it's going to write whatever. I've seen this technique being mentioned in Twitter today and yesterday a lot. So apparently this is the new hotness. This is not an info leak. Don't worry about the wording. You can read it later. But basically, if everything fails, there is still some hope for offensive researchers or for the rest of humans. It's not an info leak, but it was so cool that I had to talk about this. Basically, we have a use after free. In the attacker domain, we perform the attack. So this C element, and I'm always referring of C element bound to a JavaScript variable. So at this moment, the object is freed, but we have a reference to that object from attacker domain. The next step is to spray a lot of iframes from a target. In this case, I don't know, paypal.com, if it could be framed. I'm not sure if it can be framed, if it has the X-frame options, HTTP header or not, but let's PayPal, eBay, or I don't know, whatever. So we have in the attacker domain a lot of iframes and a reference to an element that was freed. The idea here is that by spraying iframes, hopefully one of those iframes is going to allocate that chunk with another C element. So at this moment, we have a reference in the attacker domain to an object in the targeted domain. So let's say that we cleverly select a C element, so I don't know, C table element that has a weird size, B0 or something like that. It's not something super common to be allocated. And we have an element pointing from the attacker domain pointing to an element inside an iframe. At this moment, we already bypassed the same origin policy where we cannot contain this type of links. So what's going to happen next? I will use JavaScript to insert a script tag. So the attacker domain is going to be able, through a use after free, to inject a script in the attacker domain. There are no checks for this in several browsers. The checks are in some other places. This is memory corruption converted into a logical vulnerability. Demo time. i7, Windows 7. Again, this is patched. This is not a 0-day. This is using an Infolic. Actually, it's splitting the vulnerability several times for it's going to take a little bit because this is a VMware with 500 megabytes. Heap spraying exploits the vulnerability several times, so the heap spraying is slow. But in real life, it will be quicker. In real life, actually, it's less than 10 seconds. Here is 40 seconds. And again, this is i9, Windows 7 latest bits. Instead of this patch that was released a couple of weeks ago, is the XML vulnerability you have in the slides, the CV number. Not a 0-day. I'm not 0-daying anyone. I would not do that. And you will see here calculator and the scientific one. Yeah, if you do something, do it with style. So I don't know, this deserves an applause or something like that. Thank you. This configuration did not contain any plugin. All the generic techniques for Infolics, they are all gone. Using one of the techniques mentioned before, please don't ask, I won't tell. Yeah, I'm not about sharing weaponized code with probably an unknown. So I'm going to present this CVE that is, I published a paper on March. Who has read this paper? Any of you? Some of you, right? Okay, thank you. I call the perfect Infolic because it's an Infolic in Flash that works reliably in a lot of places. So it's nominated for a Pony Award, already fixed, so I'm not sure in Adobe. Adobe was super quick fixing this before Pwn 2 on, but yeah, no, shit happens. Yeah, it's unlikely to be found by bit flipping fuzzing. It's more like API fuzzing. And there's a detailed doc in my website. So the vulnerability here is that we have a bitmap data class. Basically, it's a buffer. And there's this exposes some APIs to perform operations in this buffer. The vulnerability here is in this histogram function. Basically, you supply a rectangle, and it will give you back the histogram of that bitmap data buffer constrained by that rectangle. The idea here, the vulnerability here is that they were not checking if the rectangle was inside or outside the buffer. So you could read relative to that buffer. The idea here is that, okay, why don't I supply a 1x1 rectangle, convert that histogram to data, so I can reliably read a D word, so relative to the buffer. But reading relative to the buffer is cool. You can probably find flash pointers over there, but it's not reliable. So I'm always looking for excellence. This is what I did. I converted the relative Infolic into an absolute Infolic by performing these steps. First one, I'm going to defragment the heap of Flash. Flash uses its own heap. It doesn't use the operating system heap. And I need to massage the heap. So the initial step is defragmenting it. So I know it's going to be in a known state. The second one is this is the common heap, Flash heap state. I'm going to defragment it. Super easy. Actually, I'm using primitives of Flash. I'm using the same vulnerability as a primitive. I defragment the Flash heap. Later on, I allocate the object that I'm going to use for the vulnerability. Again, the object contains a bitmap data buffer. And I'm going to perform the histogram on that bitmap data buffer. What I'm going to do is I'm going to allocate same size blocks after the bitmap data buffer. And I'm going to trigger an heuristic on Flash to free those blocks. Remember, I'm looking for processes where I can reliably allocate memory, reliably free them, allocate objects, and heap spray. So Flash is the perfect thing. So I'm going to trigger the garbage collector heuristics. These ones are going to be freed. And what's going to happen? You see these small orange blocks? So these ones are basically linked lists. It's going to point to the next one. So guess what? I'm going to read one of those small orange squares using this vulnerability. I'm going to read the one adjacent to the bitmap data block that is pointing to the next one. So I'm going to subtract twice. Makes sense? I'm reading the first one, let's point to the second one, so I'm going to subtract twice. So I have the address, absolute address of my bitmap data buffer. And then if you have the absolute address of your bitmap data buffer, you already converted the relative infolic to the absolute infolic, because basically if you want to read 41, 41, 41, you basically subtract the address of your buffer. And by doing that, from now on comes something that is totally dependent to the platform where you are exploiting this. I made the Windows version of this. I already made the Mac OS X, but not the Linux one. And on Windows is the one that I published. What I'm going to read is the user shared data is basically I don't want to say structure because in the SDK I think it's defined as a using long. Well, basically there's on all Windows machines and is in this address 7FFE000, it's going to be an structure called user shared data, and it's going to contain pointers to NTDLL. On x86 in pointer 300 and 304 you will find in offsets 300 and 304 you will find pointers to NTDLL. This is mitigated in Windows 8. You should go to Matt Miller's and Ken Johnson's talk later on. They did a great job on this. Kudos to them. On 64-bit, that offset that it contains a null, but you can read in offset 36C of that structure the base of NTDLL. So we converted a relative infolic to an absolute infolic. We're reading this address in Windows. We start by reading the address in 32 bits. If it's a null, we assume this is 64-bit. We go to this other offset. And yeah, one of the nicest things about this is that it not only discloses the base of NTDLL, discloses where the heap is. This is Firefox. Again, this is not a vulnerability in the browser. It's a vulnerability in Flash. That's already fixed. This is Firefox. This is IE. And this is Chrome. You could apply this to Office, PDFs, that host Flash or whatever. And the nice thing about this vulnerability is that you not only disclose a base of a DLL, you disclose where the heap is. And this is going to be super useful in the 64 scenario once the operating system take full advantage of the entire virtual space. Good luck heap spraying tons of terabytes. And make the attacked user waiting for this. So once the operating system takes advantage of full entire VM space, you will not know where the heap is. And this nice vulnerability discloses both. Just final notes on what I see is going to happen in exploitation. It's going to get harder. This is because of the nice folks in the companies that develop operating systems. They are doing a super cool stuff. People that rely on common techniques, they will be left behind. They will, I don't know, start in the gardening business or whatever. The people that are good enough, they are going to be in Hawaii in a few years, or yeah, you know. And it's going to take a lot of vulnerabilities to exploit something reliably. And again, you can exploit something that works 1 out of 254 times, but if you want something reliable, you need Infolics. And several. The X number of vulnerabilities that you're going to need is, first of all, the original vulnerability. Second one, the Infolic for disclosing where the heap is, and where the second one is where you're going to need an Infolic. Probably the same one. You can reuse the same for disclosing where a module is for performing return-oriented programming. If in the next OSs they come with ways of mitigating return-oriented programming, you will need to come with a new technique or whatever. It's going to be really harder. From now on, I mean, you have seen Windows 8 Metro sandboxed with the, I forgot the name of this thing. You have seen Chrome sandboxed. Everything is going to be sandboxed from now on. the things that parses untrusted data. So you will need either a sandbox escape or an EOP, elevation of privilege. And in future, imagine that when applications run in their own VM, and this is not that of the future, there is a project called Cubes from Joanna Rutkowska, or something like that, that basically runs her browser and her email client in different VMs. So if you exploit this VM, most likely you are not going to talk to this VM, unless you have a VM escape or something like that. It's going to be difficult, but if you live up to expectations, probably you will be able to retire in a couple of years to Hawaii or someplace. At this moment, I'm going to take questions. If you are shy or whatever, you can ping me. I'm a friendly Spaniard, so thank you for being here. Do you need anything?